Okay, let's get started. Today we're going to continue on kind of that conceptual overview of hierarchical linear modeling. The focus again for that is that, or the real key behind that is this is something you're seeing more and more in educational research. And we'll see it used in terms in the context of value-added modeling, growth modeling, are variations of the same theme. Today we're going to pick up where we left off last week and get a little bit into the details of the magic behind the process, that just to kind of understand what's happening and have an appreciation for the process and why it works and what does it involve. It can be a little intimidating. We're going to see a lot of different numbers today. So to kind of start, let's kind of get in the right theme. It's going to be a little blustery.
Hum dum dum diddy dum, hum dum dum. Oh, the wind is lashing lustily, and the trees are thrashing thrustily, and the leaves are rustling gustily. So it's rather safe to say that it seems that it may turn out to be. It feels that it will undoubtedly. It looks like a rather blustery day today. It seems that it may turn out to be. Feels that it will undoubtedly. Looks like a rather blustery day today.
Okay. So we're going to really, for the first half of class, I think we're going to focus kind of more closely at the math. Sorry. Blah, blah, blah. Kind of what's behind this, what's the process. And to do this, we're going to kind of go through one more example. And using this hypothetical example, that really reflects what you see if you do this sort of research, how you would approach it in a research study. And for this example, we're going to look at this question and it's relevant for Maine because we're very interested in our laptop program. All these kids are getting laptops, and what's the impact on the kids' learning? So we have the question: does providing laptops to every student in a school increase their math skills? And you could pick any sort of outcomes, but we'll say increasing their math skills. And we're going to work with 25 schools and a total of 500 students. So every school, for this hypothetical example, we're going to have 20 students in 25 schools. So that's 500 total students. And each of those 500 students are going to be assessed 6 times. So there's 3,000 total assessments for the students. And we're particularly interested in what are those, does that laptop program impact the kids' scores? Kind of what does that school level phenomena, that school level intervention have an impact? So hold on to your piglet. It's going to get a little crazy, but it'll, again, it's not on the test. Why? Because there is no test. So we're going to be talking about these. We're going to be talking about, we've talked about betas so far, but now it gets a little crazier, a little more to it. Gammas, we're going to have gammas, betas, and pi's. Oh my. And what we're going to see with that is basically there are different Greek symbols, different Greek letters in the alphabet, but they're all serving the same function. You can think of them all as regression coefficients because they are. We're just calling them at different levels. We call them different things just to keep track. But a gamma and a beta and a pi, you interpret them exactly the same way. They're all the same. They're all doing the same thing, just at different levels. So we're going to start with this level 1 model. And in that level 1, just like we saw before, we're basically asking, are there those time-to-time differences within a child? So their test scores. Do we see test scores changing over time for the kids? And we might add some other variables. We won't in this case. That are they are they getting extra services or something that may explain variability within those? But the level 1 is really getting at that change over time within a child. And here's our level 1 equation. And the kind of in the simplest level, again, the simplest way, all we're going to be looking at here is time, is our predictor. And there's a little more notation here, so I want to spend a little time talking about it. Especially if you read some educational article talking about value-added models. The notation can be a little intimidating, but it's not that bad once you get a hang of it. We're just saying, here's y sub tij. And that's just y is the clear outcome, just like the regressions we've been talking about. That's the kid's math score. T sub tij is just a way of saying it's the math score, that assessment at time t for student I in school J. So it's just T, I, and J. It's just a way of keeping track of there's 6 assessments, T, 20 students, I, in 25 schools, J. And it's just a way of keeping track of which it's the 3rd assessment for the 18th kid in the 12th school. And we're going to see how each level of the analysis, it starts to get a little more simple. This is kind of the most complicated because we've got, 3,000 different assessments for those 500 different kids. So that's our level 1 model here. Kind of that's, as I said, in the simplest model, all we're looking at is time. We could add some other things, are they dating, are they, something that may change from assessment to assessment. But keep it simple. All we're looking at in the simplest sort of growth model is just their change over time. And we've got TI, Y, their outcome, and instead of our regression coefficients being betas, they're going to be pi's in this case. And what this model, we're just predicting their assessments, their math scores at each point in time. And visually, you can think of that. Oops. What is the problem here? Visually, it looks like this. This is that same picture we looked at a little bit ago. That it's that time for one individual child. So kind of at the model, at level 1, this is what we're looking at. Those individual assessments for each student over time. So our first question here at level 1, we're asking, do children's math skills increase over time? That's kind of a very simple question you might ask at level 1. Or is it flat? Are their math scores actually improving? Or are they kind of flat over time? So what we're doing here, there we go. We've got these 3,000 math tests. That's our y sub tij's. So there's 3,000 different assessments, each, for every kid. 6 for each of the 20 kids in each of the 25 schools. Then we have 500 for each of those students. Right? We're doing a growth curve for each of those students. So there's 500 students. And the intercept is, instead of being their beta 0, now it's a pi 0 ij. That just means pi 0, so beta 0 is the intercept. Pi 0 ij just means the intercept for student I at school J. So in other words, it's each student's individual intercept, just like we saw in the picture. Every student has a growth curve. So all 500 students will have their own intercept. And that's what this is. It's just 500 different intercepts. Every student has their own intercept. Every student has their own. What was the intercept? Their baseline score. or their predicted baseline score. So we're just predicting each individual student's baseline score. And that's what pi 0 ij is. And so we can think about it at this point. All this is, it's just saying 500 different the intercepts for each kid. You can think where we're headed with this is, oops, let me go back actually. We're going to do 500 different equations. We're not actually going to write them all out. But you can see each student gets their own intercept. So when we've done multiple regressions so far, right, we come up with one intercept term that applies to everybody. You know, there's that 1 beta 0. Here we're going to have 500 different intercepts. Every student gets their own intercept. And we're going to see every student gets their own growth curve. Every student gets their own equation, right? That's what we were just talking about. Every student's going to get their own regression equation. So even though we're writing, instead of writing 500 different equations, this is just shorthand saying pi 0 ij. It's just saying it's all 500 intercepts. I'm not going to write 500 different Billy, Bobby, Janet's, Frank's, Susan's, Dabib's, whoever's intercepts. I'm just going to write 0 ij. And that's just, the ij just is a way of saying, well, 500 of them, 20 students by 25 schools.
Would there be a need for you to write them individually?
No. No. In the old days, actually, when people first started doing this, sometimes they actually would calculate all 500 growth models and then get all those intercepts and all those and analyze them as we're going to do. But now you can do it all much more elegantly. But conceptually, you can think of it literally as here's 500 different equations. This is what it's actually estimating. We just don't see it. So you've got student 1. Here's student 1's growth curve. Here's students 2 growth curve. And I'm saying curve even though it's a straight line. All the way down to student 599. This is another one I've added. So we've got those 500 individual growth models. So going back, yeah, I know. We got the 500 intercepts, 500 slopes. Pi 1 ij is just that slope. It's each student's individual growth, how much they change over time. So they get their own growth function. And as we can see, this is a little pale. There. You can start to then ask yourself. Notice some students have low growth or slow growth. Some have more rapid growth. So we've got all those 500 equations. Your growth model, your growth model, your growth model, your growth model, my growth model. And you could actually write out all 500 of them and start to ask, well, look, this one's pretty small. That one's pretty big. This one's pretty big. This one's pretty small. You might have one that's negative. I should have done that as an example. They don't have to be positive. You could have someone that's getting worse. Yeah, it happens. You know, problems are going on in their lives. Who knows? So you have all those different growth models. And how many different... And what are these? It's important to keep on. What are those? They're not test scores. They're slopes. They're growth. They're change. It is literally change. How much they change over time. So we're not predicting, here we're not talking about their scores anymore. We're talking about their growth. And how many different growth functions do we have? Do we have 3,000? No. How many do we have? 500, because each student has their own. So we started with 3,000 assessments, but now we're down to 500 slopes for each student. And so we've got those 500 slopes, and we may take a close look and start to notice there's a lot of variability. They all don't have exactly the same growth. And maybe are there differences why this kid's got a big positive slope and this kid's got a fairly flat slope? Are there things about the students that explain why some are high and some are low. That takes us, oops, yeah, I just said that. Small slope, large slope. That takes us to our level 2 model. So far we've modeled that individual growth over time here. We've got 500 baseline scores, 500 intercepts for each kid. Kind of where did they start? Here's where we start to see some kids come in really well prepared. Some kids come in and they're not. You know, if we're starting like maybe at the start of school or kindergarten. We've got 500 slopes. Some kids show a lot of improvement. Some kids don't. Some kids maybe show negative improvement. So we've got all those individual growth functions, all those pies. And we start to ask, well, are there characteristics about the students, about the children, that says why some start off higher or lower than others? Why some have higher or lower intercepts? Are there things about the students that explain why some grow more rapidly? Why some pi 1s, pi 1 ij if we want to be technical, are more positive, are bigger than other students? So level 2 asks, with level 2, we start to take a look at each of the parameters, at each of those pies. And if we start with that first question, are there child characteristics that explain why some students start off higher or lower than other students? What we're really getting at is, are there child characteristics that explain why some students have larger pi zeros, larger pi intercepts than other students? And mathematically, here's what we're doing. We're not predicting their scores anymore. Just like we saw when we made that long list of those 500 equations and saw differences. Our outcome is now going to be those intercepts. We're not going to predict scores anymore. We're going to predict their intercepts. And ask, are there child characteristics, SES? Does SES for the child explain differences in their intercepts? Now, this then is what's called a level 2 model, because we're not predicting the outcomes anymore. Now we're predicting those level 1 growth parameters. Those level 1 coefficients are the outcome. We're predicting pies instead of test scores. And we'll see this, and we'll say pi 0 ij. We'll say pi, or just pi 0 for that intercept. We'll say pi, but what you want to say pi, but think in your head baseline scores, because that's what it is. Remember, that pi 0 ij is the child's predicted baseline score, kind of what they came in to school with. So mathematically, this is what we see, but and this is where this is where it gets a little confusing, and you have to keep track of it. You see that every time you see pi 0 ij, and you say, oh, pi 0 ij, and I tested my pi 0 ij, and here was the blah, 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 blah. But in your head, think baseline scores. We're predicting baseline scores for the kids. And seeing, are those baseline scores related to the family's SES? Visually, here's our level 1. So this is a level 2 model. To keep it kind of simple, see, now I'm confused because my hand, anyway, my copy's not up with the slides I've just added this afternoon. To keep things simple, we're going to center SES so that it's the average SES. And we're going to see why we'll do this, why we'll do that. And it'll help with some of the interpretation later on. And that's why, one of the reasons why remember we talked about centering weeks ago for interactions and some of the benefits for interactions. And I said, but that you had to do it before because the software would just crash. And there was there was other reasons, but pragmatically that was the key issue. The multicollinearity became a real problem. But there's other interpretational values that you can, by centering, it makes the intercepts more meaningful. And we talked about it then, and we'll talk about it again in a minute. So we're going to center SES in our level 2. Yeah, I know. The key here is in our level 2 model, that regression coefficient from level 1 becomes the outcome variable. And that's what you need to keep track of. That we're no longer at level 2, our outcome isn't test scores. Our outcome is going to be these regression parameters, those coefficients. It's going to be the baseline scores, and it's going to be growth. It's going to be what we're predicting. Visually, this is what it looks like. So we're back to that picture we had again at the start of class we talked about. We're looking at level 2. We're asking, here's a growth model. Here's a growth model for one student. Maybe they're low SES. Here's a growth model for a different student. Maybe they're high SES. And does SES explain differences in their intercept? With this first, that's what we're looking at first. We see, it's not specifically proposing one is higher than the other, but it's asking this sort of a question. Are there differences in baseline given the child's SES? So this is kind of what we're looking at. This is the sort of, if you can visually think of what the data looks like, kind of what you think is happening. This is what it's starting to get at. So pi 0 ij, that's just their baseline score, right? So that's what we're trying to predict. And is it influenced, are those baseline scores influenced by the child's SES? Yeah. So we start off with these 500 initial math scores, right? We had 500 pi 0 ij's, right? One for each of those 500 students. Then we're going to predict them now. Our regression equation is beta 00j. So notice we lost an I. Now, so instead of we started off with a y sub tij, student time t for student I in school j. For each student, we calculated the intercept. So the intercept, now time doesn't count anymore for the student. Right? The intercept is for each student. So it's a student in the school, the intercept 0 for student I in school j. And that's our outcome. And now we're predicting each student's intercept based on beta 00j. And so this is getting beta 00j is the school. Beta 00j is the intercept for school j. So we're looking at among all the students in that school, each school is now going to get its own regression model predicting those intercepts for all of the students in that school. So at level 1, what are we saying? We've got 3,000 assessments for 500 kids. And we're going to make 500 regression models, one regression model for each student, predicting their score. At level 2, we've got 500 growth parameters, 500 baseline scores, 500 slopes for each student. And we're going to predict those with not 500 equations now. We're going to predict those parameters with 25 equations for each school. So we say of all the kids in this school, in school number 1, what's the equation we see where we're predicting each of those 25 students, each of those 20 students, we're predicting a student's intercept, a student's baseline score based on that student's SES within the school. So each school gets its own equation. It's going to say, okay, for this school, here's the effective SES for that school. Here's the baseline score for that school. So there's going to be 25 equations here predicting the 500 individual intercepts. 25 different. So what is beta 00J? And we can think about it. It may help if we actually think about it. This is beta 00. That's your predicted outcome. And then again, because there's nothing magical. It's just like any regression coefficients. This is your predicted outcome score when the rest of the equation is equal to 0. That's what the intercept is. Well, when's SES equal to 0? Well, because we centered it, it's the average. So this is the predicted outcome for a child at the average SES. So at the average SES, beta 00J is that predicted pi 0 ij at the average SES. So you can think of, well, it's the average, so it's the predicted, what's pi 0 ij? Well, pi 0 ij, we already talked, that's that baseline, that's that initial math score. So we need to, this is where you have to start substituting in the English for the Greek. Ooh, I can do something with that. We thought pi 0 ij was that initial math level for a student. So beta 00J is the pi 0 ij. It's the initial math level when SESC equals 0. When does SES equal 0? At each of those 25 schools. Well, SES equals 0. Oh, gosh. SES equals 0 when you're at the mean SES. So for each school, beta 00J is the predicted starting value for the students at the average SES. It's kind of that for the average income at your school, what's the predicted score for the average kid at your school? So that's that predicted score for the students at the mean SES. Beta 01J then, and we're multiplying it by the SES, that's the effective SES on pi 0 ij. So that's the effective SES on pi 0 ij. It's the effective SES on the initial math levels at each of those 25 schools. So you can think of beta 0 ij is that SES effect. It's the SES effect for each of the schools. On, well, I need to be clear. It's the SES effect on what? It's the SES effect on their initial values. Because, right, that's what we're predicting. We're not just predicting their scores. We're predicting it's the effective SES on those initial values. Then, so that's dealing with pi 0 ij here, kind of those initial values. There was also the pi 1 ijs. And that was that individual student slope over time. How much each of those, we've got those 500 slopes. Every one of the kids has their own slope, their own growth function, their own growth over time. We can do the exact same thing and say, well, let's model those 500. Are there characteristics about does SES influence those slopes? And we do the same thing with another equation, another level 2 equation. Oops. Another level 2 equation where we have SES predicting pi 1 ij's, or their slope. And again, we'll see pi 1 ij, but think about that as their growth rate. That growth rate for a student. So here we're asking, does SES influence the student's growth rate? I've actually kind of tried to color code a little bit. Pi 1 ij is their growth rate. SES, that's level 1. And it's asking, does the student's SES influence their growth rate, their pi 1 ij? The beauty of this is, notice here, growth is the outcome. And we talk about wanting to analyze, do we want to look at students' growth? Do you want to measure students' growth? And we'll do it all sorts of funny ways in terms, there's all sorts of less elegant ways of trying to measure students' growth. But in this case, growth at that slope is their growth. You're literally analyzing growth as the outcome for the kids. So if you want to try to predict things that influence, what is it that influences, if you want to try to predict student growth, if you want to understand student growth, in whether it's math scores, English scores, behavior scores, anything. This does it. We're looking at growth as that actual outcome at level 2. And what variables may explain that outcome. Ooh. I tried to save some, anyway. I tried to save time in slides by putting in, but my timing's off. Anyway. Visually, this is what it looks like. Now it's that same one we looked at a minute ago. But now, when we were predicting those pi 0 ij's, we were looking at, are there differences here? Now this equation, we're looking at, are there differences in the slopes? So we have we've got these two different level 2 equations. So we had one level 1 equation. Now we've got these two level 2 equations that are asking two different questions. The first one, when we're predicting pi 0 ij, is looking at, are there differences in the intercepts? The equation that's the outcome is pi 1 ij, is looking at, are there differences in the slopes? So visually, this is what it's asking. This is kind of the sorts of questions it's asking. Are there differences why some kids show more rapid change and some kids show more flat growth? So here we go again. Pi 1 ij. We've got 500 slopes for each kid. So that's our outcome. And we're going to say pi 1 ij. But what we mean is, in our head, we're going to think growth rate. But we write pi 1 ij, but we think growth rate. Well, we'll actually write, when you do your interpretation, you would write growth rate. Okay. So we got those 500 growth rates. We've got intercepts for each school. So we have beta. Now notice the notation gets a little, here we have pi 0, so we have beta 0, 0, and beta 0, 1, which is just thinking of, it's the beta 0 for pi 0, it's the beta 1 for pi 0. Here we've got pi 1 ij, so we have beta 1, 0, which is another way of saying it's your beta 0 for pi 1, and it's your beta 1 for pi 1. Keeping track of all those little subscripts can be a headache. But there's a pattern to it. So beta 1, 0, j is the intercept which would just be that predicted slope when SES equals 0. So for each school, beta 1, 0j, we have this 25 times. Each school gets its own level 2 equation. So your school may, the average for your school may look this way, and the average for your school may look that way. It's all those, each school, like we saw in level 2, we're taking a model for every school. Every school gets its own intercept. Every school gets its own slope. And we're saying, for school number J, here's the predicted growth rate for a student who's got the average SES. I'm jumping ahead several slides, I know. Right? Beta 1, 0j is that growth rate when SES equals 0. Or SES equals 0 when they're at the mean. So it's that predicted growth rate for students at the mean SES. Beta 1j then is the SES effect in school J. It's the SES effect in school J on growth. So for some schools, the beauty of this is now you're able to say, for some schools, SES may be a big deal. And you actually see this. There's actually a whole line of research looking at this sort of equity thing. In some schools, being poor really sucks. And you see this huge SES differential. That the poor kids just struggle, they go nowhere, and as your SES increases, you do just fine. So this would be beta 1j is that effect in a school that says, boy, SES plays a big role for that school. If you're poor in that school, you're burned. If you're high SES, everything's great. In another school, SES may not have any effect at all. Hopefully it's because everybody excels. Poor kids, rich kids, everybody shows the same growth. Notice, but the key is here. It's saying they show the same growth. Doesn't mean that they're showing positive growth. Maybe it's a school that's actually really, really bad, and everyone's flat. So then you'd have to look at kind of the combination of the two. You might have, if you've got a school that at the average SES, growth is flat, and there's no SES effect, what that tells you is, well, at the average SES, kids here there's nothing happening. And, but look, there's no SES effect, so everybody's treated equally. Well, that just means high or low, they're all flat. Or you could have at the average SES, it's flat. And there's this big positive SES effect, so as SES increases, the slope increases. Or you could have at the average SES, maybe slope's positive. So your beta 1, 0j, at that average SES, the slope's positive. And as SES increases, the slope increases even more. Or maybe it decreases a bit. There's a bigger effect for the kids coming in low SES. And they're showing a really rapid improvement. And what's happening is they're just starting to catch up with the other kids. So maybe SES has a negative effect for some schools. And you need to look at kind of the combination of all of this. Kind of, what's the growth rate? What's the growth rate for the average kid? How does SES relate to that? And where are they coming in at the start of it? Where are they starting off at? And how does SES affect that? All four of those things together really are necessary to give you a picture of exactly what's happening at the school. But you see the beauty of that, instead of trying to get that one number that we see sometimes, the average for school, was it Jonestown? The average school for Jonestown, the average score is the 58th percentile. Yay, we're above average. And Jonestown was the bad school. Their average is the 40th percentile. Ooh, we're below average. This sort of growth model you're not just sticking with one number. You got like four ways of looking. It looks at the whole totality. of where are kids coming in, where are they ending, what might be explaining differences in where they're coming in, what might be how that might be related to where they're ending. You get that really comprehensive picture. Okay, so that's the effect of So beta 11J is the effect of SES on growth. Now you get to the level 3 model. Now I should put up that little piglet picture. Hold on to your piglet. It gets a little crazier. And again, you don't have to worry about this because it's not on the test, right? This is just for your edification. So if your head's a little spinning, that's okay. But hopefully the beauty is that you're seeing the potential that this offers. Not so much that you're worrying about the subscripts or beta, gamma, whatever, but the beauty and the power of the technique if you really want to understand what's happening. So at the level 3 model, now we're getting it, level 1 we were saying, change over time, kind of what's happening within that child. Level 2 we're saying, are there differences between kids? Level 3 we're getting it, are there differences between schools? So what school characteristics might explain, or I should say level 3 is asking what school characteristics may explain those differences. So not just that SES effect for the child. So in one school, SES is a big deal. In another school, SES doesn't really seem to have any effect. Now we're looking at, actually that's a child SES. Are there school characteristics that explain all of those effects? In this case, we're going to look at, for example, are there laptops? Does laptops, this school everyone gets a laptop, that school everyone doesn't get a laptop? And does that school characteristic explain growth and explain SES effects and explain change over time, explain baseline level? It can explain everything. And so how does that school level effect explain why kids may start off higher or lower, or may start off, or may show more growth or less growth over time? Now, sometimes you may expect that the school level effect's not going to have. You may think some of these things you wouldn't expect to see a difference, but you could still model them and test whether that's true. So here's level 1, right? Here's our 2 level 2 equations. Level 3, now we're adding one more level, okay, on level 3. But now, in level 1, we had pi's predicting the outcome. In level 2, we had betas predicting those pi's. In level 3, we have gammas predicting the level 2 betas, which predicted the level 1 pi's. So this is kind of makes your head spin. And again, you have to start to remember. So if you're doing this, you always have to be writing notes. And I'll tell students, I will teach a whole course on this from time to time, where I'll do I do some workshops in that as well. And one of the keys, we'll spend a couple days on it. The key is that you want to write everything down. Keep track of every single coefficient. What exactly does beta 00 mean? So that you can write the coefficient, but be ready to insert in English, what does that Greek symbol mean? So each of these 4, right, we have these 4 betas. Kind of, where do they start at the baseline, and what's the effect of SES on that? Are there differences at baseline? Kind of what's that, or I should say, what's that baseline score? Are there differences? What does SES affect that baseline score? Are there slopes? And does SES affect that? What's that average slope? And does SES affect that slope? So we've got all 4 of those betas. Now we're going to come up with equations predicting each of those 4 betas. And what is that? What's it asking? I mean, is this just fun for geeks? Or is there a question? What's the question being asked here? And these are the key questions. This is where the rubber meets the road. So, beta 00J, well, let's try to, are there school variables that explain variability in those beta 00Js. Now remember, what was beta 00J was, and it's color-coded because I keep track of that, that's that effect, that's that baseline score, right? That's that baseline score for students at the mean SES. So kind of that average student at each school, what's their baseline score? That's what beta 00J was. And it's a J. The J tells us, oh, that's right. That's those J schools, those 25 schools. There's 25 beta 00Js, and we're going to try to predict those based on whether those 25 schools have laptops or not. So in this equation, this level 3 equation, tech sub j is just, does that school number j, those 25 schools, do they have laptop? And I'm just doing tech just to keep it, it's shorter than writing out laptop. So we're coding this. This is just a dummy variable. We're coding 0 if it doesn't have if it's not a one-to-one school, and 1 if it is a one-to-one school. So that's level 3, and now it's color-coded green. So we got green, red, and blue, just to kind of keep track of the different levels. Visually, here's what we're now describing. Now it's a little more complicated, and you can't really. I could put it into one picture, but it would be too messy. So what we can think of is what we're asking is, at this first model, what's beta 00J, is we're asking, it's students, we're asking, do those one-to-one laptops explain variability, or explain why those students at the mean SES, right, those average students at a school, start off higher or lower, kind of at that mean SES, kind of how are they doing? So here, is there a difference? We can think of it visually. We got one-to-one schools and non-one-to-one schools. So here's the average for non-one-to-one schools. Here's the average for a laptop school. And we're asking kind of, are there baseline differences? So in this case, you might think, if you do a nice intervention, you kind of want all this. If you're doing an intervention, it would be great if we'd gone in and been able to just randomly flip a coin, and maybe the first year half the schools get a laptop and half don't, and you kind of flip a coin, and so there's no difference in those baseline characteristics. Of course, the world doesn't work that way. But so that's okay. You may expect that there's no difference, but now we'll actually test. This will start to examine whether there's a difference. If you're a laptop school, you're starting off higher. It's a school with more resources to begin with, so gosh darn it, they went out and bought those laptops. They weren't going to wait. So there may be differences at baseline. But again, what are we doing? It's for those we have to remember. It's for the students who are at that mean SES. It's specifically. Here's the average growth for students at that school at the mean SES. So kind of those baseline differences. So beta 00J is their baseline, kind of the starting point, kind of where average kids started for school. Average meaning in terms of income. That's that initial math score for students at the mean SES. Boy, see, that's why you really want to write these down, so you can literally cut and paste to keep track of. That's our initial math level at the mean SES, and now I'm predicting it. And you want to kind of keep track of that. I'm predicting it. Gamma 0, 0, 0, now it's gamma 0, 0, 0, because it's the intercept It's the beta 0, 0. It's the intercept 0 for the beta 0, 0. So it's one more 0, no j. So there's just one. This is across all the schools. What's the intercept for all 25 schools? When it's that predicted beta, well, gamma 0, 0, that's your predicted beta 0, 0. It's that predicted score, that predicted value, that predicted beta when tech equals 0. When does tech equal 0? That's the non-laptop schools. So gamma 0, 0, 0 is the initial, right? It's that initial level at the mean SES for non-laptop schools. Right? Because beta 0, 0j was that predicted, that initial level, that initial math level at the mean SES. Specifically for and gamma 0, 0, 0 is that predicted baseline level at the mean SES specifically for non-laptop schools. So that value is it's calculating that baseline for the kids in for the average kids in non-laptop schools is going to be estimated by that gamma 0, 0, 0. This is the tech effect. That's that laptop effect. Or how much does that baseline score increase if you're in a laptop program, or a laptop school, I should say. So gamma 001, this gamma is the effect of laptops on, where you got to keep track of the language. It's the effect of being in a laptop school on what? That initial I should have still maybe kept that. Well, no, because now we're talking about the gamma 001. But it's the effect of being in a laptop school on beta 00j, which was that initial math level for students at the mean SES. So you kind of put it all together. I know it's messy. You put it all together. It's the effect of being in a laptop school on the initial math level for students at the mean SES. So do laptop schools, is there a difference between laptop and non-laptop schools on where their kids are starting at the beginning, on average, where their kids are starting at the start of the study? This is where you see my school's getting burned because, for whatever reasons, our kids are starting off lower than the intervention kids getting whatever because, well, now we're going to get at why that might be the case. Then there's beta 01j. Now, what was beta 01j? I have to flip back the slides because you wrote this down. But that was the SES effect on initial levels. It's not an SES effect on slopes. It's the SES effect on those initial baseline levels the kids have. So do kids in your school, in one school, everybody starts off the same, and maybe kids in another school, there's a big SES differential. High SES come in really high, low SES kids come in low. At some schools, in other schools, all the kids are coming in about the same. You know, they've got some great preschool programs. All their kids are coming in about the same, ready for school. You know, so are there those differences? That's that. Beta 01j was the SES effect on those initial levels.
In your opinion, how does this compare with the ugly and the good and the bad ugly thing that we talked about?
This is the Medusa. Right? Wasn't she the one turned to stone? Really ugly. Snakes there. It's really, but in the same sense, the uglier it gets, the more powerful and the more accurate it gets. If you really want to understand, and you can hopefully start to see, and this is why I think education's often been reticent to do this. It's messy. It's complicated. And we're just even touching on, we haven't talked about these little errors at the end. There's parts that we're not even worried about. That really it's complicated, but it's very ugly. but it's powerful and it gives you the right answer. If you really want to understand what's the effect of a big intervention on individual kids, you've got to do it this way. And if you really want to make sure that the Cape Elizabeth schools just don't always look great, and they can do a mediocre. No, Cape Elizabeth may be doing one because we got our Portland group down. They're probably doing a phenomenal job. But if you don't want to reward some schools that may be doing just plugging along and not showing much growth, but gosh darn it, they start off so high, I can be a lazy teacher and do nothing, and my kids are still going to score above the 90th percentile. And it's not because of me. And that poor teacher at Jonestown who's working her butt off, and those kids are showing a lot of growth, but they're still below average because they came in completely unprepared. And you don't want to burn them, and you want to really reflect, good job for Jonestown, and you guys need to get your act together. If you want to be able to do that, this is where you do it. This is how you do it. So here we're looking at those differences in the baseline. Does the laptop program influence the SES effect on baseline programs? And that's really kind of messy. The SES, right, we're looking at one-to-one laptops explain why the SES effect on students' initial levels differs from school to school. Visually, this is what it's looking at, and we got 2 slides to illustrate this because this gets messy. In other words, what you might see is something like this. Let's say this is our non-one-to-one schools. So we look at the non-laptop schools, and maybe we see, oh look, there does seem to be an SES difference among those maybe 12 or 13 non-one-to-one schools. At the baseline level, kids who are low SES are coming in, and again, we're just focusing on the baseline. Those low SES kids are coming in the non-laptop schools. The low SES kids come in somewhat below the high SES kids. There does seem to be some difference in the non-laptop schools. In the laptop schools, look, and we're just focusing on the baseline. Here's the growth functions for the laptop schools. The low SES kids are coming in much closer, much less of a difference between the low and high SES kids in the laptop schools. So there's some difference going on here. There's something between the laptop and the non-laptop schools in terms of the kids coming into them at the start of the intervention. Now we can statistically, the beauty of this is we statistically control for that, and we're back to, okay, that's going to make the interpretation a little complicated because we get to that issue of, is everyone flat because they're all doing well or they're all doing poorly? It complicates the interpretation. But the beauty is we're doing all those individual growths, so we're able to, the information's all there somewhere. Just interpreting it at the end is going to be complicated. But this is what this gamma is looking at. Are there differences? Does the SES effect and baseline scores vary based on, are you in a laptop school? Laptop schools, SES really doesn't make much of a difference on baseline schools. Non-laptop schools, SES seems to have a big difference on initial levels. So beta 01J, we're predicting, you have our level 3 equation, predicting those beta 01Js. We got 25 of them. Each school has its SES effect, right? That's what beta 01J, what was that again? See, I'm already forgetting. What was beta 01J? Oh, it was the SES effect on the students' initial levels. So let's put it down. It's the SES effect on the students' initial levels for those 25 schools. Gamma 0, 1, 0 is, well, that's the predicted SES effect on initial levels when tech is equal to 0. When's tech equal to 0? The non-laptop schools. So gamma 0, 1, 0 is the SES effect in the non-laptop schools. In the non-one-to-one schools. I should do the slides first because in case I say it wrong, it's nice. It feels good to see it's confirming what I've just said when I do that. But to play it safe, I should actually put the words up first so I make sure because you can see, and this is why it's why it scares people. It is so easy to interpret this wrong. You can see it's tough. So gamma 0, 0, 1, 1, that's the laptop effect. It's dummy coded. That's the difference between non-laptop and laptop schools. So gamma 0, 1, 1 is the laptop effect on, what is it? Beta 0, 1J, on the SES effect. So that's the laptop effect on the SES effect. Or it's the difference between laptop and non-laptop schools in the SES effect. If gamma 0, 1, 1 is not significant, it tells you no problem. There's no difference in the SES effect between the laptop and non-laptop schools. Maybe SES does influence where the kids come in. No Nobel Prize in that one. But the laptop program doesn't seem to be influencing that, which would probably be a good thing because at least you know your intervention's not systematically going to a different type of school. This is a case where no intervention effect on your baseline score is probably a good thing. The schools are all basically the same, whether they get the laptops or not. At the start of the study, they're all basically, these are talking about at the start of the intervention. They're all basically the same if there's no tech difference. But we've actually tested it now, and now we're not relying on me coming before you and saying, oh, trust me, they were all the same. I've seen people try to get away with that. That's a problem in education and other fields. We've done that. We do that too much. We'll go and try to convince people to do stuff, and it all comes down to, trust me, they were all the same. Now you can actually go and say, I'm sorry, what was your gamma p-value test result? You tested it? Oh my. Did you really? Are you sure? How do you know they're really the same? Then, so that's those two. Then we've got the beta 1, we've got our second our second level 2 equation where we were predicting the growth functions. We had our 2 betas there, and we can do a level 3 equation looking at, does the laptop program affect growth? This is what we're really going to be interested in. The first one's nice because it's a good way of understanding, do we have problems at the start? Did we start off the project kind of with weird differences between our schools? And what are they if we did? Here, it's actually testing, okay, did laptops affect growth? And how did it affect growth in the kids? This is what we're spending all that money on. So we have to go back and say, okay, what was beta 10J? And I flipped through my slides because, God help me, I can't remember what it is. And I say, oh, that was the beta 10J was the growth rate for students at the mean SES. So that's that average growth rate for schools, kind of for the kid for the average kid at the school. Because this is being filmed, I know this isn't. There's more subtlety to this. If anyone goes on to take my HLM course, I know, but we're keeping it simple here. Don't worry, unless you take the class. It's a great class. So that's that average. You can think of it, that growth rate, kind of that for the average kid at the school, is what beta 10J is. So we've got 25 of those. Each school has its own kind of average growth rate, or growth rate for the average kid at the school. And we're going to predict those 25 growth rates based on are they a laptop school or not. Visually, here's what we're looking at with this first one. So is there a difference? We've got our growth rates. We're asking kind of, is there a difference in these slopes for average kids? So these are the slopes for the average SES and a child in the average SES in a non-laptop school, the slope for the average SES for a kid in a laptop school. Are those slopes for those average kids different between for kids at that mean SES? So we're predicting beta 10J. Again, that's that growth rate for a student at the mean SES in 25 schools. Gamma 100 is the predicted beta 10J when tech is equal to 0. So it's that predicted beta 10J. It's that predicted growth rate at the mean SES when tech equals 0 in a non-laptop school, in a non-one-to-one school. Put it all together, gamma 100 is that growth rate at the mean SES for a non-laptop school. So that's those non-laptop schools, here's that average growth rate that we saw. A nice, beautiful number. Isn't it just, that's what gamma 1's, that's that average growth rate for average kids in non-laptop schools. Hot dog. Then gamma 101 that's that tech effect. It's dummy coded. So that's the difference between a 0 and a 1, between a non-laptop and a laptop school. So that's the laptop effect, right, on those average growth rates. Oops. So that's that laptop effect, the effect of being in a one-to-one school on what? On the growth rate for students at the average SES. So gamma 101 is answering the question, on average, do kids in laptop schools show more growth over time than kids in non-laptop schools? In that key, is everybody improving in non-laptop schools? And this is, or are kids in non-laptop schools improving? And this is how much more or less are kids in laptop schools improving? And you can do a statistical test and determine, is that a significantly different degree of improvement between laptop and non-laptop schools? Then it gets, the beauty of this, you can get a little more elaborate. Well, what about SES? Right? We have beta 11J. Remember that beta 1 back in our second level 2 equation. That second level 2 equation here, we had beta 11J. That was the SES effect. What was it? It was the SES effect on growth rates. So does laptops, so there's that SES effect on growth rates. Remember, in some schools we realized, SES played a big role on growth. If you're in school X, and if you're high income, you're high SES, you show great growth, but if you're low SES, you don't show much growth. So there might be, or you could be in a school where SES doesn't play much of a role. All the kids are showing good, solid growth. So beta 11J is that SES effect on growth rates. And we can now do a level 3 model that asks, does the laptop program impact the SES effect on growth rates? Now the beauty of this, it's getting, and this is, I think, I'm not sure how well this has ever been articulated in the state's whole laptop program, but this is getting at, not at all. 622. I need to delete that. This is getting at the question, kind of the key question of maybe the laptops can diminish that SES effect. Does giving kids laptops help to remove the penalty? Does it help everybody? Maybe we started off, maybe we saw a big SES difference, and laptops helps to wipe that difference out. So the low SES kids are differential. Maybe they're really starting now to improve. Give them a laptop, and their growth rate gets closer to the high SES kids. So maybe laptops don't really play a big deal for all the kids. I mean, heck, I think we've commented. We have more computers at home than people, and we're above average SES. So a laptop for our child, it's like which one? Other than it's kind of he likes But for other kids, if they're low SES, this might make a big deal. And so maybe what laptops are doing, it's equalizing. And so if you look overall, maybe laptops really aren't having an overall effect, but maybe it is having an effect on improving those for low SES kids. That would be that would be pretty cool.
Even if that's true, how would the school be able to afford laptops for all the students?
Well, that's another issue. How do you fund? I mean, that's your problem. How do you fund this sort of stuff?
It actually is, yes.
Yeah, but that's what this equation's getting at. Does it change if there was this SES effect, beta 11J? Does laptops help to diminish that SES effect? This is the sort of question I get all excited about. It's in essence, and what we're getting at are interactions. Does this variable change the effect of that variable on that variable, predicting that? It's complicated in the math, but the question is fairly straightforward and a beautifully elegant and powerful question. And here's how instead of me just coming and saying, trust me, oh yeah, it really helped those poor kids. Trust me. And, come up with the $30, $40 million based on my word. Or, here's some data that we can really test it and show it really did help those kids. So, visually, here's what it looks like. Now we're getting it, okay, here's non-laptop schools. Now, what do we see? This is to illustrate and again, this isn't specifically what's being hypothesized, because the statistical test is just going to look, is there a difference? But this kind of illustrates the sort of difference that it's getting at. That if we look here, here's the difference in the slopes between high and low SES students. And, there's a pretty good, let's make sure I'm interpreting this right. I'm not going to have to contradict myself in just a second. Yeah. Here, notice there's a pretty big difference in the slopes. For non-laptop schools, kind of the business as usual school, low SES kids are showing very little growth. High SES kids are showing more rapid growth. So the effect of SES there's a definite SES effect on the slope. From a 0 to a nice positive number based on your SES. But in the laptop school, look what happens in this example. The slopes are almost the same. Now there's no SES effect on the slope. If anything, look, the SES effect's a little opposite. The growth for the low SES kids is actually a little higher. It's a little stronger for those low SES kids because they started off a little lower and they're finishing almost identical. So that's what this is getting at. Does the SES effect change? Does the school level variable change the effect of SES? So we think of all the challenges kids come to school with, and this is how you look at, does my intervention to deal with whatever, fill in the blank, help to compensate for fill in the blank problem that the kids are coming into school with. Poverty, lack of resources, family disruption at home, developmental disabilities. What are all those things that the child level they're coming in with? And does my intervention, my program, my laptops, my counseling, my whatever, offset those challenges that they're coming in with? These are the kind of the key questions of education. And it is a level 3 effect. So here's that SES effect on education. Oh, SES effect on the, see, it's good I wrote it down. What was it? The SES effect on growth rates is beta 11J. Right? The SES effect on those growth rates. Gamma 110 is that expected SES effect on growth rates when tech is equal to 0. So it's the SES effect on growth rates in non-laptop schools. And gamma 111 is the laptop effect, the effect of being in a laptop school on the SES effect on growth rates. I mean, we're talking about effects on effects on effects. But again, that's gamma 111 is, does laptops offset? Do laptops help to diminish the effect of poverty or whatever on students' growth over time, so they take less of a hit? That's what that's getting at. That is HLM in a whirlwind. Again, it's not on the test. There's not, I'll tell you, there's no homework on this. Not for this class. But it's actually, it's not that, if you sat through one of my workshops on this or my class, I mean, you start to, it's the same stuff, really. It's you notice gammas, betas, pi's, oh my, all those subscripts. There's a lot there. But once you've done it a few times, the real trick is just to make sure you write down what you write it right from the beginning. You write down, what does that pi mean? And then when you do level 2 and you've got betas now predicting pi's, okay, I take that pi, I take that language, that English, stick it here, and now I'm adding a little bit to it. Oh, it's the high SES, it's the low SES, it's the SES effect. Now that's what that beta means. And then I go down to level 3. Now I'm doing my gamma. I take that text, and now I modify. So you end up with fairly cumbersome language, which is kind of annoying. But it's accurate and helps you to identify exactly what's the question I'm looking at. And there's lots of answers buried in all those gammas. There's a lot of answers. SES, time, are there time differences? Are there SES differences? Are there school differences? Do the laptop, are there laptop differences? Does laptop help offset SES? What's, everything's in there. So very valuable stuff that we should be seeing. And I think in that sense, it's a good thing coming out of Washington. I think that's been pushing more of this sort of accountability. That again, you're not just relying on me coming and telling you, oh, trust me, it really helped these kids' growth over time. This is, and it's the right way to do it. Because there's lots of wrong ways to try to do this that we do all the time, all too often. This is kind of the right way if you really want to look at growth over time. And again, the beauty of it is, right from the start, as we get to that level 2, your outcome is growth. We talk about wanting to look at kids' growth. Here, growth is the dependent variable that you're modeling, which is beautiful in a geeky sort of way. Let's take a break.